Hello everyone, welcome to this online class. I am Francis Okech and my YouTube channel is Professor Francis Okech. Today we are going to look at Calculus 2 and our topic is techniques of integration. We will look at the third technique, that is trigonometric and hyperbolic substitution. Before we look at the trigonometric and hyperbolic substitutions, I want us to recall the trigonometric and hyperbolic identities. So we know that cos squared theta plus sine squared theta should be equal to 1. That is trigonometric identity. When it comes to hyperbolic, we'll say cos hyperbolic squared theta minus sine hyperbolic squared theta should be equal to 1. Another one is 1 plus tan squared theta should be able to give us sec squared theta. That is another trigonometric identity. When it comes to hyperbolic, we'll have 1 minus tan hyperbolic squared of theta is equals to sec hyperbolic squared theta. Mostly we are going to be using these 4 identities. You can call this number 1, number 2, number 3, number 4. These are the most useful. I'll tell you how to apply them when it comes to integration. So we are going to look at some forms of integrals, and then I'll be able to show you how to apply these identities. So the first form of integral, I can call it part A. Let's say integrals of the form the integral of 1 over x squared plus a squared dx. A is a constant, take note. X is a variable and a is a constant. So in this kind of integrals, how are you supposed to proceed? You can take note where take note here that a is a constant. So how do we go about this kind of an integral? Remember, this integral can be rewritten as, if I factor out, remember when it comes to integrals, it is possible to factor out the constant so that we integrate the variable. The constant can be factored out. So this integral can be rewritten as, you factor out a squared so that we have 1 over a squared, then the integral of 1 over, we'll now have 1 plus x squared over a squared. You see what I've done? I have factored that out, the a squared from the denominator, so that our integral can be written as the integral of 1 over 1 plus something squared. So which trigonometric identity should we use here? The substitution. Look at identity number 2. 1 plus tan squared theta is equals to sec squared theta. I'm going to do the comparison. You take note that 1 plus tan squared theta should give us sec squared theta. Now in our denominator here, the whatever we are integrating, the integrand, we have 1. That means a different color. In our integrand, we have 1 plus x squared over a squared should give us something. So just compare the left-hand sides. What can you say? 1 can be compared to 1. So we can easily say that tan squared theta is the same as x squared over a squared when you do the comparison. So from here, we can say that x squared over a squared is the same as tan squared theta. So when you make x the subject in this equation, you get x, of course, x squared is equals to a squared tan squared theta. So therefore, we are going to say that x is equals to a tan theta. So the x is equals to a tan theta. This is the substitution that you need to make. When you have such kind of integrals, this kind of form, this is the form of integrals that we have there, then to be able to work it out, you start by saying let x be equal to a tan theta. So what is the derivative of x? So you have to find dx, d theta, because we must also know how the differential dx will change. So dx over d theta, that we remember is a constant, so differentiate tan theta, which is sec squared theta. So there we'll have a times sec squared theta. And if you make dx the subject, you're going to get dx is equals to a sec squared theta d theta. So those are the substitutions that you make. Look at the ones I have bracketed. These are the substitutions that one has to make to be able to solve or to evaluate such kind of integrals. The ones that I have ticked is what is important. So I am going to give you just one example to illustrate the concept. For instance, let's say we are asked to evaluate this integral. Can call it the integral of 1 over x squared plus 4 dx. So here, what do you think is our a? In this case, because it is x squared plus a squared, so our a must be 2 because a squared is 4. So you can write this, that we take note that a squared is equals to 4. So this means that our a must be equal to 2. So we let x be equal to 2 tan theta. What about dx? So you can say therefore our dx will be equal to 2 sec squared theta d theta. You differentiate x with respect to theta so that you get that. Now, when you substitute it back to your integral, this is what you're going to get. Our integral will now be the integral of 1 over, now we know x is equals to 2 tan theta. If you square that, you get 4 tan squared theta. There's another plus 4. And we also replace dx by 2 sec squared theta d theta. You see in the denominator, I can see there's 4 common. And in the numerator, there's 2. So it's like there's 2 in the numerator and 4 in the denominator. So this thing can be now written as 2 over 4 outside. Then what do we remain with? We remain with the sec squared theta d theta in the numerator. And our denominator is now tan squared theta plus 1. I hope that is clear to everyone. Now, what is tan squared theta plus 1? Go to our identity number 2. We said tan squared theta plus 1 is the same as sec squared theta. So you'll find here that that tan squared theta plus 1 will cancel out with the sec squared theta, so that our task is now to integrate 2 over 4 is the same as 1 over 2. So right there 1 over 2 times the integral of the theta. And this should give you 1 over 2 theta plus a constant c. Now that is our answer, but we have to replace theta. So where do we get theta from? Check where you defined your theta. We said let x be equal to 2 tan theta. So from here, check the one I've bracketed. From there, you can make theta the subject. It means theta is equals to, because I'm going to divide by 2, so that I have x over 2 is equals to tan theta. So to get theta, you take tan inverse on both sides. So theta is tan inverse of x over 2. And so when you replace it back to our solution, we get 1 over 2 tan inverse of x over 2, then add c. Remember, c there is a constant of integration. You see how this thing is very simple? As long as you know what to substitute, then your work becomes very easy. I will look at another one, another example. You can call it part B. You are asked to evaluate this integral, the integral of 1 over x squared plus 10x, and then that is also added to 30 plus 30 dx. So how do we go about this? Again, you have to write that in the form of x squared, or simply a variable squared plus a constant squared. 1 over variable squared plus a constant squared. So what you do here, you see in the denominator x appears in 2 terms. I want to combine those into one thing. And in the denominator, we have a quadratic expression. So to be able to combine those 2 terms involving x, what I'm going to do is complete the square in the denominator. And how do we complete the square? This is what we do. You know that x squared plus 10x plus 30, this is 10x plus 30. This can be written as x squared plus 10x plus a certain value which I'm calling c. This will be grouped as one thing. Then there is plus 30. You see, I've added c, so I have to minus the c. You add c and you also subtract c. So how do you find that c? The c here is usually given by b over 2 squared, where b is the coefficient of x. So in this case, our b is 10. So 10 over 2, that is 5. When you square it, you get 25. So that is our c. So this thing can now be written as x squared plus 10x plus 25. Then there's 30 minus 25. Now, the first bracket is a perfect square, or simply you can be able to factorize that so that you get x plus 5 squared, x plus 5 squared, perfect square. And the other one, 30 minus 25, that is the same as 5. So you see the way we've rewritten that. Now, we go back to our integral. it means our integral can be written as the integral of 1 over x plus 5, that is squared, and then there's another plus 5 dx. Again, you see this again is in the form of a variable squared plus a constant squared. We compare. In this case, our a squared is 5. So what is a? A is root 5. So you can write that a squared, we take note NB, that a squared is equals to 5, which means that our a will be equal to root 5. So what do we do? It is the whole of this. This is the whole of the variable x plus 5. That is what you say, because we said if it is just x, you say let x be equal to a tan theta. Here it is now x plus 5. You're just going to say let x plus 5 be equal to a tan theta. Let x plus 5, I hope that concept is clear, is equals to a, which is root 5 tan theta. See, let x be a tan theta. In this case, now it is x plus 5, which will be equal to a tan theta. And we have said a is equals to root 5. So when you differentiate this with respect to x, you're going to get on the left-hand side, of course, you differentiate on the left-hand side, you get dx is equals to root 5. Derivative of tan theta, that is sec squared theta. Remember, we are differentiating with respect to theta. Somebody may be asking, why have I not written plus 5 on the left-hand side? 5 is a constant. When you differentiate a constant, you get 0. Remember, it was dx d theta, which after cross multiplying, you get what I have there. So let's substitute these two into our integral. So our integral will now be written as, instead of x plus 5, I am now going to write root 5 tan theta. And remember, it is x plus 5 squared. So this integral will now become 1 over, so we square root 5 tan theta, that will give us 5 tan squared theta. Tan squared theta. Then there's another plus 5. Dx, you also have to replace. Dx is root 5 sec squared theta d theta. And if I factor out the constants, I can see there's root 5 in the numerator. There's 5 common in the denominator. So this thing can be written as sec squared theta d theta over tan squared theta plus 1. And what is tan squared theta plus 1? That is what we have said is the same as sec squared theta, identity number 2. So those two will cancel. And so what we have here is root 5 over 5 times the integral of the theta, which if you evaluate, you get root 5 over 5 theta plus a constant c. So that's our answer, but we have to replace theta. So check where we defined our theta. It is this one here. And make theta the subject. So it means you start, first of all, you start by dividing by root 5, so that we have x plus 5, everything over root 5 is equals to tan theta. And then make theta the subject, so take tan inverse on both sides. So in this case here, if you make theta the subject, you get theta is equals to tan inverse of x plus 5 over root 5. So our final answer is that it will be now equal to root 5 over 5 tan inverse of x plus 5 over root 5, then plus a constant c of integration. I told you when it comes to definite integrals, don't forget to add the constant c. That is indefinite, where we don't have the limits of integration. And one last example on this kind of integrals is, let me give you, we call it part C. Just a simpler one. To make you understand the concept better, you are asked to evaluate the integral of 1 over, that's now 1 over 2x squared plus 12x plus 32 dx. So how do we go about this? The hint here is that you have to complete the square in the denominator. And before you complete the square, remember, when you're completing the square, the coefficient of x squared must be 1. So even before we complete the square, it is advisable that we rewrite this integral by factoring out 2. Why are we factoring out 2? To make the coefficient of x squared 1. So this thing can be written as 1 over 2, then the integral of 1 over x squared plus 6x plus 16. I have factored out 2 dx. So complete now the square in the denominator. What will this be? Take note, when we complete the square in the denominator, it will be this way: x squared plus 6x plus 16 can also be written as x squared plus 6x plus a number c. And I've told you how to find c. Then there's a plus 16 minus the same number c. How do we find c? Remember that the number c that we need is equals to b over 2, and this is squared. The b here is the coefficient of x, which is 6. So 6 over 2, that is 3. When you square that, you get 9. So our c is 9. So this is the same as x squared plus 6x plus 9, then plus 16 minus 9. And so when you factorize the first bracket, you get x plus 3, and that is squared. 16 minus 9, that is 7. So our integral can now be written as equal to 1 over 2 times the integral of 1 over x plus 3, and that is squared, then there's plus 7 dx. So what substitution do you make? What a squared is equals to 7. So what is a? So in this case, you let x to be equal to, not x, but now you see it is x plus 3. So I'm going to let x plus 3, not x. Check the whole of that. I hope that is clear. So we say let x plus 3, the whole of that bracket, be equal to root 7 tan theta. So you need to know the derivative. So what about dx? It will be equal to root 7. When you differentiate tan theta, you get sec squared theta d theta. Remember, we are differentiating with respect to theta. That's why I'm adding the d theta. Or you could write dx over d theta is equal to root 7 sec squared theta, and then you cross multiply so that you have dx as the subject of the formula. So we go back and substitute that in our integral. So this will be equal to 1 over 2 times the integral of 1 over 1 over, now instead of x plus 3 squared, that should give us now 7 tan squared theta. Plus another 7. Instead of dx, we have said that is root 7 sec squared theta d theta. If I simplify this, I factor out the constants, I'm going to get root 7 over 14. And then inside we have sec squared theta d theta, everything over tan squared theta plus 1. And you know, tan squared theta plus 1 is the same as sec squared theta. So the whole of this will cancel with this. So what do we remain with? We remain with root 7 over 14 times the integral of the theta. And this should give you what? Root 7 over 14 theta plus c. And what do you get when you replace theta? We need to know what is theta. So you go back here and make theta the subject. Go back to this one. To get theta, we first of all divide by root 7 so that we have x plus 3 over root 7 is equals to tan theta. Then take tan inverse on both sides so that you have theta is equals to tan inverse of x plus 3 over root 7. So this will be root 7 over 14 tan inverse of x plus 3 over root 7 plus c. So that is when you have integrals of the form 1 over a variable squared plus a constant squared. And the idea here is that the substitution which you have to make is 1 plus tan squared theta is equals to sec squared theta. That is the identity that is guiding us to know the substitution to make. In that case, it is x is equals to a tan theta. So I hope everyone has understood that concept. This marks the end of this class. When we meet next time, we look at another form of integral where we have to apply another trigonometric or hyperbolic identity. So thank you for your time. Have a good day. Don't forget to like my channel, to subscribe, even to watch, comment, and even share. Bye-bye.